So let's get into a few more practical aspects of how to prescribe the ocean-atmosphere interface in terms of heat exchange, right? So thermal boundary conditions are what determine that. So you have a flux going from ocean to the atmosphere. So you set a sign for the exchange. If heat flux goes into the ocean, you can make it positive, and if ocean is losing the heat flux to the atmosphere, you can make it negative. There is no fixed convention, or you can flip the signs as well. But if you write it this way, then you have a shortwave component where the energy is coming in. So that is written as -1 minus alpha 0 alpha ocean, times Q short. We're putting a minus sign here because we are writing atmosphere to ocean as positive, and here we are writing ocean to atmosphere. I'll just get used to it, okay? And there is a long wave radiation from the ocean to the atmosphere, so it depends on ocean's emissivity and ocean temperature, so sigma T0 to the fourth, if you remember well. Minus, you have also long wave back radiation from the atmosphere, so I have to be careful, into the ocean, so that's negative. So emissivity of the atmosphere, sigma Ta to the fourth, plus some sensible heat exchange, so the temperature difference between the ocean and the lower part of the atmosphere that's interacting with the ocean has a sensible heat dependent on the temperature difference and the coefficient D. Actually, it should also be dependent on wind speed, which is done in some cases, plus the evaporation from the ocean, which is a cooling effect, latent heat loss. Technically, even precipitation should be included, but usually it's just the latent heat loss due to evaporation, which is going to depend on ocean temperature and atmospheric temperature as well. So the average albedo of the ocean is about 0.2, and emissivity of the ocean is 0.96. Emissivity of the atmosphere ranges from 0.7 to 0.9, and this sensible heat exchange coefficient is typically chosen to be 10 watts per Kelvin per meter squared. So now you know what we mean. We have heat exchange between the ocean and the atmosphere, but it's not something we measure directly. We begin to represent them with these kind of parameterizations because we know that the sensible heat exchange depends on the temperature difference between the ocean and the atmosphere. We know that the evaporation also depends on the temperature of the ocean and the atmosphere. So we have to approximate those, and of course things like emissivity are obtainable from the estimated from measurements or lab studies, but these kind of coefficients here have to be measured in various indirect ways, and a parameter has to be picked, or we will see that there are ways to also optimize them based on other larger scale observations. Okay, so here is the atmosphere, and here is the interface of the ocean and the atmosphere. So this is the diagram of different model parts and fluxes of water, heat, and momentum. So you have evaporation happening, so equation of water vapor affects the atmosphere, which affects the thermodynamic equation and radiation balance, which affects the equation of motion, which affects the surface stress that is driving the ocean. So there is also sensible heat that is exchanged and directly affecting radiation and thermodynamic equation. Precipitation and evaporation are affecting salt equation and sea ice equation for the ocean. Radiative transfer is affecting the ocean thermodynamic equation, and wind stress is affecting the equation of motion. So this is the kind of exchange that has to happen in the physical space between the ocean and the atmosphere. And we are not even saying anything about the time scales here. There are time scales from very short seconds to minutes to hours to diurnal cycles to seasonal cycles, intraseasonal time scales, decadal, multi-decadal time scales, and so on. But main thing to remember is that the atmosphere has a very low heat capacity, so warms and cools very rapidly, has low density, so can move very fast, which means it can move energy very fast in the lower level of the ocean atmosphere interface as well. But the ocean is much heavier and has a very high heat capacity, moves much more slowly. So those kind of time scale mismatches also have to be worried about. So this is the challenge of modeling. At what time scale and what spatial scale information is being exchanged, and how that representation of sensible heat and penetration of momentum into the ocean has to happen, and so on. Plus there are exchange coefficients involved in formulations of evaporation, as we will see in a minute. There is a chopper going by. Okay, so there are actual couplings involved that we have to worry about. What the atmosphere gives to the ocean, what the ocean receives from the ocean, and so on. But you can get some sense from here looking at annually average heat fluxes in watts per meter squared based on comprehensive ocean atmosphere data set. It's based on that because we estimate, so we take basic measures of temperature, humidity, winds, and we compute heat fluxes. They are not directly measured. Okay, areas with heat fluxes exceeding 60 watts per meter squared are hatched, and the zonal averages are shown here. This has a lot of information in it because here the ocean heat flux is positive by our definition of atmosphere putting heat into the ocean. Why is it positive there? Because that's where the trade winds create Ekman divergence and upwelling and cold temperatures. So cold temperatures are created by ocean dynamics, and the atmosphere is trying to damp the SSTs constantly. That heat via circulation gets carried through western boundary currents to the latitudes where the atmosphere is much colder than the ocean, so ocean is losing heat. So this convention here is not done with colors, so you have to be careful. Here the numbers are negative and here they are positive. So in this convention, ocean receiving heat is negative, ocean giving up heat is positive. It doesn't matter, as I said before. So this has a lot of information in the sense of why there are differences in amount of heat going into the ocean here versus here, why the pattern of ocean heat loss is different here than here, and what that means in terms of evaporation, precipitation, salt left behind, density of water that is created, and so on. And Indian Ocean is always warm, as we saw, so it is receiving heat even though it's warm, whereas here ocean is receiving heat because it's cold, and it's losing heat here because it's warm. So you have to determine what are the processes that decide where the heat is going into the ocean, where it's coming out of the ocean, and how that changes from season to season, year to year, and so on. Okay. Plus also on longer time scales, there has to be a global balance. Amount of heat going into the ocean has to equal the amount of heat coming out of the ocean. So if you take negative and positive numbers and average over the globe, that should become zero at some time scale. There is a time scale. So then how do things change here and here? Do they change on the same time scale? Of course not, because the heat has to be transported from here to there and lost here. So changes here don't immediately get communicated over there. But then what is the time scale? That relates to two things. One is the ocean transport and the other is the atmosphere transport. Remember we talked about heat transport, so that's something to worry about. But that kind of balance can be seen here, where there are negative numbers, where there are positive numbers in the zonal mean, and what is the amount of energy being transported in the ocean towards the poles. So there is divergence towards the poles from the low latitudes. and that has to be explained in terms of the physics as well. And this is the same figure but showing the Atlantic, where you again have energy going into the ocean where temperatures are colder, energy coming out of the ocean where the ocean is warmer, and atmosphere is picking up the heat from the ocean. That leads to cooling of the ocean through evaporation, which leaves salt behind, which creates the North Atlantic deep water in this region, and so on and so forth. So there's a strong coupling between the energy exchange at the ocean atmosphere interactions, large scale circulation, large scale heat transport, and so on. But of course the time scales are very critical there. Okay, so let me leave this here, and then we will come back and look more specifically at the formulations for different components of the fluxes. So the flux itself has short wave, long wave, latent, and sensible. So we will look at each of those, and or how the ocean models represent the net heat flux exchange in some circumstances, depending on what processes you are trying to study. Okay.